Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. We're in section 215. Now, in the previous little subsection, we were considering certain types of merges, and we were showing that these preserve the operations of union and intersection. Now, we're going to assume that we want two different subsets in our power set represented as codes of zeros and ones. If we happen to merge those two together in some kind of merge map, and we know at least just those two are merged together at minimum, but we also know at minimum that the operations of intersection and union must be preserved, then what do the fibers look like? What else is merged together? In fact, in particular, what else is merged to these two subsets? Okay, so we're going to use some notation here. We're going to use a bar right here to represent which chunk or which fiber each subset is in the merge. Like for instance, this guy is going to have the same image as this guy. That's what that means. It's the same chunk. Okay, they're in the same chunk here in a fiber box partition, if you will, of this merge. All right. So now, what does it mean for this merge to preserve intersection and union? I mean, here's another description of that. Pretty much that, and I'll kind of notate this a little bit to kind of help us think about this. Just kind of write this out a minute. So if we have, so A intersect B, it's going to be the same thing as, so doing it before is going to be the same thing as doing it after. Now, which means this chunk, A could be, you take anything in this, you take anything in the chunk that A is in, and anything in the chunk that B is in, and you put it over here. And you take their intersection and look at that chunk, that should be the exact same chunk as whatever chunk that we had for this. Which means that this chunk should be the exact same no matter how we change the representative for A, so the same chunk that A is in and the same chunk that B is in. So basically what we can do is we can do replacements. So we're going to do two things. We're going to if two things have the same image like this, that means that when we're doing bars like over top, then that means we can replace what's under the bar. So what's in the pre-image, if it's going to have the same image, under, replace what's under. And the second thing we can do is we can use this idea that that the bars split over the operations that they preserve. Okay, so before or after means you can move the intersection, you can kind of split the bars. So if I can write that there, split bars. So we can do these two things. We can split bars and we can replace under. And if we do those two things and work on that, then we can come up with different types of relationships to determine what must be in the same fiber. Let's look at some examples now in the text and see how this goes. All right. So we'll keep going here. All right. So for instance, well, here's just an example. Let's look at this chunk here, the chunk that has 1, 0, 0, 0, 0. Okay, so this one right here, what also must it contain? All right, and all we know is that these two guys are going together. All right, now why did we choose that? Well, if you think about it, it's, let's see. Well, we'll keep going and see here as we go. So we have this is equal to this, all right, which is one of our sets. It's this one right here, union with 1, 0, 0, 0, 0, or intersection with. So that's an intersection. So intersected with that, which makes sense, right? Because this is a subset of that, because it contains, because this is completely contained in there, and take the intersection, it's just going to be that right there, right? That's just a simple statement we can make. But think about our replacements. Okay, and also kind of imagine that there's bars over top here. We can replace this, and maybe I'll draw some in as we go, so we can kind of think about that. So we can replace this with this, okay, before we actually apply the merge, all right, and then we'll still have. Okay, so whenever we have whenever we have bars, we can make replacements, right? So we can make, so here we can make a replacement. We replace this with this, and when we intersect, we actually get this. But these two guys have to be the same, right? So those images have to be the same when we make replacements. So, wow, well, that means that 0, 0, 0, 0 is the same as this. Oh, this is the empty set, right? Hey, that means that this merges to empty. Interesting. We picked something that merged to empty. Okay. Well, that's kind of an interesting thought. All right. So let's keep going here. So that means that those two guys are in the same chunk. All right. So we can compute. Okay. And here's some other examples. So here we have 0. Okay, 0, 1, 1, 1, 0. So that's, I guess, another one of our. So that's these two guys were being merged together. All right. And think about this is the intersection of this and that. But let's replace this, all right, with what it's being merged with. And this means you get the empty set. Hey, that means that these two guys are in the exact same fiber. If we drew lines over the top, they would be in the same, they'd be equal, they'd be in the same chunk. In fact, you can see that right here. So what does that mean? That means that, so they're merged together. All right, so empty set. So we're kind of, I guess what we're doing is we're collecting things that are going to be in the empty set, or that are going to merge with the empty set. We got that one and we got that one. Okay, so let's try only replacing the empty set with those two guys while using the union operation. Let's see what happens. So we take, okay, so like take a subset like this, and it's going to be equal to that union something else, right? But we can intersect it. Well, we can replace this with this and get something else that'll be in the same fiber as this guy. In other words, put a 0 there. So really, whether there's a 0 there or a 1 there didn't really matter, right? They were in the same fiber. It's almost as if there's a block there, maybe, in this merge that we're considering. Well, food for thought. We'll keep looking at that. So we'll do this in 2 more steps. Okay, so we take this. Okay, so let's look at this particular subset and look at it. We're just kind of pulling out different examples and just kind of experimenting right now. So there's really no, and then as we go, we're kind of making some observations. So we're just kind of trying some things out, picking some subsets almost randomly, it seems like right now, but we're making some observations off of them. All right, so let's take a look at this one. So this one is this guy, union with that, right? But these two guys are replaceable, right? Because they have the same images in the merge. So replaced by that, and then this whole thing should have the same image as that, right? Because unions are preserved in here with the bar here. And so we can replace the parts in the union and then put the line over the whole top, which is the line over that. So that means that those two guys have the same are in the same chunk. Okay. And likewise, it looks like it. Looks like it. In fact, this is kind of what we're getting at. Anytime that you know you that everything outside of these blocks are the same, they're going to be you're going to be in the same fiber. And if you just ignore that, so this really is a block out merge, and we kind of we're getting that by just looking at um, what the empty set had to merge with, what its fiber was. Um, and we just looked at some examples, but kind of for illustration to at least motivate what needed to happen. In fact, we're pretty much done. Why? Because we know a blockout merge preserves union and intersection, right? We also know this particular blockout merge merges those two guys together that we wanted at the beginning, right? It merges these two. This particular mock blockout merge merges those two, and um, we showed just minimally, just assuming that it preserved unions and intersections, just with a few examples of observations that we actually um, that no matter what we did, we were always ignoring those, right? So meaning that it was at least as good as the blockout merge, and so it must be. All right, so we're pretty good. So we got it. So we actually figured out a blockout merge. Now, the question is, how did we know it was those particular elements? Why were we blocking out those ones? If we wanted to merge, uh, if we wanted to merge the those two together that we were originally thinking about. So notice this one, the 1 and 0, they're different, right? And also this position, 0 and 1, those are the two positions that are different there. It's almost as if you take the positions where these guys are different and just say, hey, let's put a block there and cover up their difference so we don't see their difference anymore. And here, see this 0 on the front there, and that 1 there on the front. Those are different. Let's cover up their difference right there at the front. So we're covering up the difference right there in that position and that position. So that's kind of how we can do it. We have two things. We know exactly which positions to block out because we're just saying like, well, which ones actually make a difference, right? And then we want to cover those up so we don't see the difference. And then we know they have the same image. Then we get the merge, and then we're done with that particular description. Here's a little bit more that kind of describes this. We're basically ignoring blocking out any entries, right, where they are different. Okay, so yeah, you're looking at um, um, any code position corresponding to a 1 in A union B that is not in A intersect B should be blocked off. So this kind of picks out those differences. Okay, so, and this describes it a little bit more, and that concludes that little subsection 215. Thanks for watching.